So yeah, let's start our lecture today, and so okay, yeah. So let's start with this one. Okay, so okay, so since yeah, so last time we'll stop at here. So this in this executor is Hausdorff. And then this y2 is not on the orbit of this y1 on the gamma, and y2 is not the action of gamma on this y1, and then for each okay. Okay, so for each element, each element small r in this gamma, gamma 1, we may choose neighborhoods, neighborhoods PR and QR of okay, PR and QR of R y1 and y2. Okay. Respectively that are disjoint. Okay, so respectively that are disjoint okay, so let me see. So okay, so okay. Yeah, so because yeah, so this is true because this executor is Hausdorff, and these 2 points are not the same, so therefore we can choose distinct neighborhood. Okay, we can choose distinct neighborhood. Okay, and then okay, so thus okay, so thus okay, we get neighborhoods okay. Okay, so this R1, which is being defined as B1 intersect the intersection of R in this gamma 1 are inverse of this PR. And then for this R2, okay, which has been given as V2 intersect the intersection of R in this gamma 1 of QR. Okay. Of this Y1 and Y2 respectively. Okay, so and neighborhoods. W1, which is being defined as the projection of this R1, which is subset of U1, okay, and then this W2, which has been defined as this projection of this R2 subset of U2 of x1 and x2 respectively, of x1 and x2 respectively. Okay, so let's see why we can choose such neighborhoods. Okay, so we just pick the neighborhood, right? So we just pick because here, okay. Yeah, so for each element R in this gamma 1, right? So we pick this corresponding PR that corresponds to that element R, right? And then such that, yeah, and then we take the R inverse of this set, and then which is open set, yeah, and then we take the intersection, which is a finite element, which is open, and then V1. So what is V1? Let me check what is V1. So, oh yeah, so this V1 is like the, okay. Okay, so this V1 is like the connect component of, it's a component of gamma inverse of this U1. Okay, so okay, so okay, so remember that we proved last time that this gamma is actually a covering projection, right? So therefore, for any x1 and x2, we can pick the evenly covered kinetic component, yeah, of this U1, U2 of this x1 and x2. Okay, so here this U1, U2, they are the evenly covered kinetic components. So and then V1, V2, they are the one of the component, yeah, one of the component of the disjoint union of the pre-image. Okay, so okay, so yeah, so here, so this is like okay. so this is like R1, and then this is like we define R2, okay, and then okay, and then this so this PR, so this PR is a neighborhood of this RY1. Then you take the R inverse, that becomes the neighborhood of Y1, right? And then same thing, so this QR is the neighborhood of Y2, okay. So this is like a neighborhood of Y1 and Y2, and then and then this W1 so this W1 is being defined as R of this projection of this R1 onto this U so on this U on this subset of U1, and then this W2 is being defined as the projection of R2, okay, inside the U2 of this x1, x2, okay, good, okay. So now let's see. Okay, so now the neighborhoods. Okay. W1 and W2 are disjoint. Because so because you take this gamma inverse of W1 intersect with gamma inverse of W2 intersect W2 is equal to so it's equal to so this gamma acting on this R1 intersect R2, okay. Okay. So so let me do this. So which is also equal to the gamma 1 acting on R1 intersect R2. And then, so this whole thing is a subset of union of R in gamma 1 PR intersect the intersection of R in gamma 1 of QR, which is empty. Okay, so let me see. neighborhoods, okay. Okay, so, okay, 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 so let's draw some pictures. So, here we are picking, okay, so we want to show that this X is a Hausdorff space. So here we pick any 2 points, x1 and x2 here, and then we pick a, so the previous setting allows us to give like a evenly cover the neighborhood, let's say u1 of this x1 and u2 of this x2, okay. So at this point, we are not sure whether their intersection is empty or not, okay. So just as, yeah, so we just say that there exists such a evenly covered neighborhood, and then for this u1, I think what we did is that we take this relatively compact neighborhood, the v1 of this y1, I think. And then this u2, I think we have the v2, right? This is y2. Okay. Okay. So, and then, okay, so what about, okay. So, okay, so then, because, yeah, so this is x tilde, right? So this is like x tilde, this is like x, okay. So now, okay, so for each element R in this gamma 1, we can, yeah, so we can choose neighborhood PR and QR of this. Okay. 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 So here, so think about that. This is like the R of y1, and then, yeah. So for each R of y1, right? Because this is like the fibers, right? Because they are the same element under the, yeah. And then, okay, so this is R of y1. So we pick a neighborhood PR and QR of this R of y1 and y2. Okay, so think about like, so yeah, you can pick like a, so this is the identity, right? So P, let's say identity here, and then maybe let's say, and then this is like a Q, okay. So this is like the Q of the identity map, and then okay, so here let's pick another like PR here, and then maybe another, yeah, QR. Sorry, this is a little bit, yeah, okay. Maybe I erase the y2 here, and then instead I write it here. Okay. Just imagine that you pick many terms like that. Okay. Maybe like R. Yeah, just okay. 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 So okay. So now this R1 is what? This R1 is V1 intersect this. Okay. Okay, yeah. So basically, this is like, because you do so this is R of y1, right? Then you take the R inverse, then you get a, let's say, R inverse of PR here, okay. Yeah, so this is the R inverse of PR. And then similarly, you do like another, so for example, this map is like R prime, and you do another R inverse like PR prime or something. And then you get that. Okay. Yeah, okay, so here you get R1 by taking all these intersections. Okay. And same thing for the R2, right? So R2, you just do the intersection of this R in this gamma 1 of this QR. Yeah, you do the intersection with a V2, right? And then you do a projection. Okay. Yes, you do a projection onto W2. Okay. So this is like a W2 here. So here is like W1. Okay, so we want to argue that these two are disjoint, right? Okay. Yeah, so yeah. Okay, so now okay, so why they are disjoint? So okay, I want to show that gamma inverse of W1 intersect gamma inverse of W2 intersect V2 is equal to okay. Okay. Oh. Okay. 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 So yeah. So this one. Okay. So imagine you take out everything out of the intersection. So the things that you get here is like this R1, right? And then everything left. Imagine you take out the intersection, and then here you get R2. Okay. So okay. So here. Okay, I want to show that. Okay, I want to show that this gamma inverse of W. So okay, so okay, so maybe let's show that. Okay. Okay, so let's show that. So show gamma inverse of W1 intersect of W2 intersect V2 is equal to this group action of R1 intersect R2. Okay. Okay, so let's say that you pick any element x. Okay. Okay, so x in okay, let's call this A. Okay, let's call this set B. Okay, so if x is in A, this implies that so x is in both this set, right? So x is gamma of 1 and x Okay, so this implies what? This implies that, okay, gamma x is in W1, right? Okay. Okay, and then this is also in W2, right? Okay. Okay. And then okay, x is in V2, okay. Okay, so y is in this set. Okay, yeah, because this equivalent relation is in W1, right? So yes. So okay, so what is W1? W1 is this projection of R1, right? So yes. So this implies that okay. So okay. So since this W1 is equal to this gamma of R1, so then this, okay, so then we have this is in gamma of R1. Okay. Okay, so this implies what? What is gamma of R1? So gamma of R1 is let's say x prime is R1 such that and let's say let's use R in this gamma such that x is equal to okay power of x prime. Okay. Okay. So this shows that this x is in okay. And then y okay. Why this x is in R2 then? Okay, because x is in V2, right? Okay, so why x is in R2? Okay. So I want to show x is in R2. okay, so namely we want to show that this x is in this set, right? So it's the equivalent of saying that this x is in QR for each R in this gamma 1, right? Okay, so y is true. So why this is true? Why is in this QR then? So this okay. So this QR is like the neighborhood of this point, right? Okay. So here we are picking the x to be. Oh, okay. Okay. So this because this x is in gamma inverse of W2. Yes, exactly. So therefore, therefore what? So because x is in gamma inverse of W2. So oh, okay. Okay. So this implies sorry, I write here. So okay. So this implies that this x is like so this implies that the equivalence class of okay. So this implies that gamma of x is in this W2. Okay. Oh, okay. 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 Yeah, we have shown that this because so here because okay okay, so basically by the so because this U2 is like the so if we do the because okay, so this U2 is like even so this W2 is also an even cover set, right? And so therefore we take the pre-image, right? So it should consist of disjoint union of the open sets. Okay. So then what we do is that because here we also know that this x is in V2, right? So therefore it must lies in this must lies in here. Okay. So this shows that okay. And then okay, I think this just shows in this direction. And then so for the other direction, so if you have x in this R2 intersect this wait, okay. So so let this just automatically implies that x is in W2 and then x is also in, sorry, x is in V2 and then x is also in gamma inverse of W2, right? Yes, okay. Because, okay. And then gamma inverse of W1. Okay, so what's left is to show that y is x is in gamma inverse of W1 because this x is in, okay, because this x is in this set, right? Okay, so yeah, I think yeah, because x is in this set, so therefore it can be related by this gamma to an element of inside this R1. So if you, after you take the equalization, that's gonna, yeah. That's gonna be in this W1. Okay, so okay, I think it shows. Okay, and then for the next one, so y is equal to this part. Okay, so okay, let's take the same x again, and then oh okay. Okay. I think this is because yes. So this is because. So remember this this gamma is this R1 is compact, right? Yeah. So this R1 is like a pre-compact. Wait. Wait. So we know that this V1 is relatively compact, right? So so if you take a closure, is any closed set of compact set? A closed set. Yes, I think so, right? Wait. Give a closed set of a compact set. Give a closed subset of a compact set. Take the should be open. Oh, yeah. So why is compact? Closed set. Closed subset of set. Okay, I think this set is also compact. Yeah. So this is compact. Okay. And then yes, and then you have that yeah, so this is also compact. Okay, this is also compact. And then yeah, because you take the closure, they are all compact. So because of the proper discontinuity of this gamma, right? Because wait, these are wait. Want to be a little bit careful here. Okay. Okay. I want to be a little bit careful because this R1 they are not compact set. Oh, shoot. Okay, I see. Okay, I see. So here, okay. 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 So, by definition of this gamma 1, okay. Okay, we know that. Okay, so this is what we know. Okay. So, yeah, I'll just erase this part. Okay, so we know that okay. Hmm? Wait. Okay. Okay. Okay, so we know that this R of V intersect V is empty for each element, for each element R in this gamma, take away gamma 1, right? Wait. Okay. I know that this gamma 1 is acting. Yes. So this is how you define you fix the point. Oh, okay. So, yeah. Okay, so this gamma 1 is being defined to be the set where, okay, yes. So, yeah, okay. So here, this, okay, we know that, okay. Okay, so remember we defined these gamma, yeah. Okay, so we said K, okay. So okay, so let K to be the set V1 closure in union V2 closure. Okay. So this is a compact set. Again, okay, and then we know that, okay, we say that this R of K intersect K is empty for each where each r in this gamma, take away gamma 1. Okay. Okay. So yes. Okay. 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 I think this is true. Okay, this is true. Okay, okay, this is true. Okay, again, okay, so here, what about here? So, okay, so why this set is contained in here? Okay, so we have the union of, okay, so here, let's take, okay, so I'm trying to show the last part. Okay. So you take any x, so let's call this C. So x in C, okay. Oh, okay. So, okay, x is in, okay. Yeah, because x is in, so